All right, another question on exercise 10.6. So this is our series and parallel reactions in our isothermal batch reactor. So we won't bother discussing this too much. We'll just jump right into the code I received. But I just want to make a note that, again, all we're trying to do is look at different relative values of our pre-exponential term and then compare, series and parallel behavior with these different relative values of our pre-exponential terms. And then we're going to plot selectivity and concentrations as a function of time, and then compare that to what we had found for our CSTRs before as well. So there's no need for F0 or things like that where we're trying to find, say, time for a particular concentration. And then I'm just going to have open up that section on batch reactors in case we need to pull any details out. Okay, so I maximize this. This is the code I received. So I have a function with no inputs. Outputs R1, R2, NA, and B and C. So R1 and R2, yeah, you could return back the rate at a given time, but let's see. And it looks like they're going to manually specify relative values. Okay, fine. Okay. All right, so let's look at this. So RTE. Rate expressions, that's good. Okay. So if I just look at this, parallel and series, I mean, this is exactly the same, right? So you really don't need to have a second case for series. As far as getting my rate constant, it's my rate expression that's going to change. Okay, so this ODE45 call isn't quite going to be right. Why it's not going to be right is if I just have a single output variable L. Okay, remember ODE45 is a function that uses multiple optional output variables. So L is just going to end up being time, right? So what I want back is, well, let's just leave L for now. But well, no, we don't want to, right? Because L is just going to be time. And actually, I see this is where you're playing around with concentration, and you could return it. That's fine. Okay, but let's do this. Let's return T and Y. Okay, now just based on this is concentration of A. All right, 2400, and then this will be concentration of B and C. Okay, let's unpack resulting matrix. So let's do concentration of A. Okay, this would be Y, all rows, first column. Concentration of B, B all rows, second column. Concentration of C, all rows, all rows, third column. Okay, cool. And then we'll come back to plotting and things like that, but let's take a look at my rate function. So CSTRDE, okay. So you unpack L, okay, that's good. Okay, so let me make this L, right, to be consistent. So before, when you're just using L as your output variable, again, the reason it wasn't right is your first optional output variable is T. All right, so you're just gotten a vector of times, not your concentrations as you thought you were. So you unpack L, okay, parallel, you got your stoichiometric coefficients. It's beautiful. Okay, you have a separate case for series where you just need to comment them out. We can play with that. Mole balance design equations. Okay, this is good. Okay, but now res here, you need to pack up your rate expressions. You're not packing up your concentrations, right? So basically, L then would be an input to your function and output. It doesn't make much sense. Okay, you want this to be my rates. Bam. Okay. So good. So this should be a valid call to get this animal to work. Well, kind of. Okay. We've got some more playing around to do. Okay, so the first thing then, so you unpack, bam. So this is really going to be concentrations. So let me go ahead and relabel these as concentrations of A, B, and C. Okay, because this you're getting at concentrations. So I'm going to relabel this as differentials of concentrations. I'm going to pack these up as concentrations. Okay. And so why I'm going to do that is if I were to pop back over to batch, okay, remember my rate expressions, okay, so you have these, you have your mole balance design equations right, okay. Now, the one thing that I did is I renamed these concentrations. So you could think of V as a constant, factor it out, bring it over to the left-hand side, factor into my differential. Moles of a species divided by volume just gives you molar concentration. So I'm going to get rid of V by writing everything in concentrations. And why that's going to become useful is, remember, R is going to be first order in, for parallel concentration of A in both cases. But then I'm also going to need these rate constants K1 and K2, which I computed up here. All right, so what I need then is I'm going to need K1 and K2, which you define above. Okay, and we'll worry about that in a second. Why? Because R1 is going to be equal to K1 times CA, and R2 is equal to K2 times CA. Alright, so my rates are both first order in A. Okay. So now R1 is properly going to be K1 times CA, and R2 is K2 times CA. Okay, beautiful. Okay, and then just what I need to do is, how do I want to do this? Up. So my rate function, I added K1 and K2 as inputs. So what I need to do here is I'm going to create an anonymous function to pass K1 and K2. So I need to get K1 and K2 to my rate function. So let's call it CSTRDE K. I'll just do K. And that'll be equal to, okay, this is going to be a function of, we use T and L, and that value of T and L, I'm going to call CSTRDE. I'm going to pass it that T and L along with K1 and K2. Okay. So then this would just become this anonymous function, which I also pass K1 and K2. Okay. And then just, my proof this works. So I'm going to add a plot. I'm going to plot T versus CA. We'll just T versus CB. Okay. And, you can go ahead and update the labels and all of that fun stuff. But just proof to you that it works. Okay, so let me just add a legend, since I chose to let MATLAB automatically color everything. Okay, so just to give you proof that this works. Okay, bam. If I run this, right, I should hopefully get a plot. Hopefully this should work. It's taken a long time. Just peeking to make sure I haven't didn't break anything. Okay, let me go ahead and I'm going to kill that. That's a long time that's taking. So let me look up here, just make sure I have everything. Okay, so K naught this is units of seconds. One thing is this exponential term is going to be dimensionless. So this is in kcals per mole. Okay. So let's convert E to joules per mole. So E would be A in kcals. 1,000 gets me to calories, and then it's 1 calorie is 4.184 joules. Okay, so let's see if that's just it. Yeah, okay. So that last thing that was keeping it from running is I just updated, or the activation energy was in the wrong units, right? So yeah, so it works. You can go ahead and add labels and make that look pretty, but hopefully that gives you an idea. But while I'm at it, just for fun, let's take a look at 2 other things. Okay, remember they want you to look at selectivity and different values of relative values of k naught. And so if we think about different values of k naught, let's make molt, right? So molt is my multiple, so that k naught 2 is molt times k naught 1, right? Let's make that multiple an input. Could we do that? And yeah, the answer is sure. So instead of 0.1 here, we could just make molt an input. Okay, and since you're passing K1 and K2, that should be all that you need to do. So there's 0.1, it's 10, right? Cool. So you can make multiple an input. The way you have the code set up, you could also add a flag to check for series or parallel. So let's do, when flag is 1, we'll do parallel. When flag is equivalent to 2, series. Okay. So what we need to change. So if I look at this, okay, reaction 2, right, this is just my rate constant, so that's going to be the same if it's series or parallel. So you don't really need that. Okay. But what's going to happen is what I want to do is I just need to update my rate expression. So I'm going to add flag as an input to my rate expression. Okay. And add it to my input line here. Okay. Okay, so all I did is get flag all the way down to my rate function. And then this is what's going to change, right? So here's my, so R1, all right, R1 is going to be R1 whether I have series or parallel. Okay. So rate 1 is the same whether I have series, whether I have parallel or series. Let's keep it rolling. All right, but what's going to change is our stoichiometric coefficients and our second rate expression. So let me just do an if flag is 1, that's parallel. Okay, so use these values of my stoichiometric coefficients and use R2 is K1 or K2 times CA. Right? I think that's how I label it. Otherwise, if flag is 2, that's series. Okay, so then for series, I'm going to use this set of stoichiometric coefficients. Okay, and then R2 is now first order in B. Close up that logical block. Because then that should be exactly the same. Okay, so I can run it. Right, and so let's go to the case of 0.1. Parallel, flag is 1. Okay, looks like I forgot a semicolon. So semicolon here. Okay, so again, a parallel 0.1, parallel 10. Let's do series 0.1. Okay, looks like I just need to increase the time, so having run that, and maybe you want to make time an input. It's totally up to you. I'm just playing around with your code here. So series with 0.1, right now I can see that extremum. Yeah. Series 0.1, trying to make sense of myself if the results look fine. Oh, series 10. Now this one, the time would be much smaller. Okay, hold on. Just trying to look at this. But so now I can make that an input and things. So we convert there. It does look fine. Yeah, nothing's jumping out to me. For some reason the plots look a little different, but nothing jumps out to me as being wrong. So I'm going to assume that they look okay. Yeah, but here I am now. I can choose the multiple and whether or not I want to do series or parallel on the fly. CC is underlined because, well, CC is not actually in my rate expression or used, but it's okay. We'll solve for her anyways. But hopefully that gives you an idea and gets you going. Okay, and you could you can build off of this, and you should build off of this and make it look nicer. And then remember, look at the problem statement where they want selectivity as well as a function of